Today I'm going to talk about negativity, um, and I'm going to start by reviewing some basics about negativity and as an entanglement measure, and then talk about random tensor networks and a little bit about holographic duality. So can you hear me with this volume? Okay, good. So this is an ongoing work with Xidong and Cypher Nezami and Michael Walter. It's really ongoing. Some of the results are like half a day old. So let's start from some reviews of entanglement and negativity. So basically, like when we say entanglement, we really mean anything that tells me the state of some system is not a product state. I mean, of course, I'm drawing a bipartite case. More generally, it could be multipartite statement, but basically anything that distinguishes product states with other states can be considered as an entanglement measure. But more precisely, you want something that's invariant, or sorry, maybe not increasing under local operations and classical communication, as you heard from Tadashi's talk already. So you can find the different measures that tells you how much quantum entanglement there are, and the simplest one that we are most familiar with is entropy, and then you also have like Rényi entropies. And for example, Rényi entropy is related to a trace of a reduced density matrix to some power, and you could write that in a form like that. I'm just emphasizing this because this is very helpful for later of the talk. Like, for example, a Rényi entropy, you can write as some expectation value of some operator in k copies of the system. So this is not true for general invariants like the von Neumann entropy. You cannot write this way, but these kind of polynomial invariants are nice because, at least for my purpose, they are easy to calculate. Like they are not linear operators in the original system, but they are linear operators in k copies of the system. And more generally, I want to mention that we can consider a large class of invariants, which are local unitary invariants. The definition is a little bit different from the entanglement measure, as we mentioned the local operations and entanglement and classical communication. So if we simplify the problem by just by looking for invariants that are invariant under local unitaries in each region, then it's mathematically easier to find. And this is an example. Like if you do a unitary in this region A or region B, it's an invariant. And of course, there are many of them because if you count how many invariants there are that satisfy the symmetry, it grows exponentially with the size of your system because this unitaries acting on each subspace is on each subsystem is much smaller than the unitary group of the whole system. So you have many such invariants. Most of them we don't know anything about. And negativity is another invariant like this, which is slightly more sophisticated than entropy. So it's defined like this. So you take a density matrix, and this is supposed to mean in the same convention as Alexei's talk. This is supposed to mean a matrix that acts on these two legs, give you the other two legs. So that's a matrix acting on system A and B. And then partial transpose is defined as you just take these two legs and permute them. So that defines another matrix, which is still Hermitian, but generally not positive definite. So when you look at the eigenvalues of this matrix, these are all like local unitary invariants, just like the original eigenvalue. Like the transpose do not violate that local unitary invariance. So you can just look at these eigenvalues lambda and any function of them. These will be some local unitary invariants. And for example, you can imagine something like this. Like you can have eigenvalues which change after the transpose. Like before you transpose, it's a density matrix, so it has some eigenvalue between 0 and 1. After transpose, it may become negative or not, and this is where the name comes from. And when the eigenvalue becomes negative, then there is some qualitative difference between these states. More precisely, so this one reason the negativity is interesting is like if all these lambdas are positive, like if this doesn't happen, the eigenvalue do not become negative, then the state is not distillable. It means you cannot distill EPR pair from it. It means basically the state is mainly just some classical correlation between the two parties, and there is no much quantum entanglement. For example, if you have a separable state, it means the state is in some density matrix rho IA and some density matrix rho IB with some probability, and these different rows are orthogonal. So this is separable state, and that basically means the state actually has only classical correlation. It's just in that state I with probability P I. So if that happens, then this is certainly 0 because the transpose doesn't change the eigenvalue. Okay, so that's just some brief introduction on this quantity. And why is it interesting? And there has been a lot of studies in negativity in field theory and in holography. So for example, I'm listing some example of works, including Calabresi, Cadi, and Tony, and also there's a work of Mukund and Lota in 2014, where they talk about both holography case and the field theory case, and there are some more recent works from Sengupta and collaborators. So I'm going to mention some of the works later. Okay, so a little more comparison is just like entropy. When we go to from polynomial entropy to Rényi entropy, we can do the same thing for negativity. Instead of looking at this log negativity, which is a sum over absolute value of lambda, we can look at these power k quantities. As I said before, these quantities are sort of nicer in some sense because they are expectation values of operators in k copies of system. And once you have these quantities, you can analytically continue it back to what you want. Like you can take even k, so that this quantity only knows about the absolute value of lambda, and then you take n goes to 1/2 analytic continuation, then it gives you the log negativity, which is the sum of the absolute value. Right. So that will be 1 if it's not negative. So log n will be 0, but if there's negative eigenvalues, it's non-zero. But also I want to emphasize that with these lambdas, you can define other quantities, some other analytic continuation, and this quantity turns out to be useful in the later part of the talk. So this quantity, for example, we can look at the odd n, the odd k rather than even k, so the odd k quantity knows about the sign of lambda, and then now if you take analytic continuation back to 1, this quantity goes to 1 because it's the trace of the transpose. It's the same as the trace. So that's 1. But then you can do the same thing as the entropy case. You take a derivative of that, right? And then you get something that looks really like an entropy, except these lambdas are not positive. Like the sum over them is 1, but they are not positive. So they are not probabilities. But this quantity turns out to have a better holographic dual than this one, actually, as we'll see. But keep in mind that we can define different quantities to describe properties of these eigenvalues, lambda.
What is the relation between this other quantity and entanglement?
Between this one and the entanglement?
Yeah. No, an entanglement, I mean, if it's not entangled, it's also 0 or something like that?
I think that's not true anymore because, So this one is like 0 if I have some eigenvalues that are moving, so it's not separable, but it's still positive. The lambda is still positive, then this is 0. But this one will become non-zero. I mean, this one will deviate from the entropy. Like what we actually should look at is this transposed entropy minus the original entropy, because it was non-zero even for separable states. Because if the lambdas are eigenvalues of density matrix, then it's like the original entropy. So the difference between this quantity and the entropy of the state is a measure of how the state is not separable. But it doesn't have this property that it's 0 if it's not distillable. So it's not distillable if it's 0. It doesn't have that property. Okay, so just similar to the Rényi entropy case, you can do a you can write this replicated negativity as some expectation value of expectation value of operators in k copies of the system, because like this quantity is polynomial in rho. I'm just changing how I contract their matrix elements, but it's still polynomial in rho, right, with power k. So so you can write it this way, like in a so let's say if you take 4 rows and then transpose each of them and then contract. So this is like row, 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 and then transpose and contract. Then you can write this in terms of, you first just prepare 4 independent copy of rows. So that's the direct product. And then you, if it's linear, you would just cyclic permute all the copies and contract them. But here, there is this partial transpose, which is done by cyclic permute the other leg in the opposite way. Like this one is the cyclic permutation, and the other one is the opposite cyclic permutation. If they are the same, you just get trace rho to the k. Okay, so that's how you get the nk, and these xk's are cyclic permutation operators, and this is x dagger, which goes to the opposite permutation. And okay, so just to give you a little bit intuition for those of you who were not familiar with negativity, let's look at the example which is like 2 qubits. So for example, if you have a maximally mixed state, of course it's separable. So the eigenvalues of density matrix is 1/2, sorry, is 1/4, and it's trivial. And then you can interpolate from that state to a EPR pair state of 2 qubits. And that one is pure and it has an entanglement, it certainly has a negativity. So you can interpolate between the two, and then you look at how the eigenvalue of density matrix evolves, and you find that one eigenvalue becomes bigger, the other becomes smaller, and then it crosses 0 somewhere here. For some reason, the axis is not showing nicely. So it crosses 0 somewhere here. So from this point on, there will be a negativity. And if you look at the Rayleigh quantities, for example, I'm taking one particular p and plotting this Rayleigh quantity, the Rayleigh negativities, then they kind of oscillate. So if you do analytic continuation, you should do it separately for the even ones and the odd ones. And the even ones will extrapolate back to k equals to 1 to some finite value, and that's the log n, that's the log negativity. And then the odd ones will extrapolate back to 0, but you can take the derivative here. That's the thing we were discussing in the previous slide. Any questions before I move on? Okay, so now now let me start to talk about the random tensor networks, where we will study these negativity properties. So these random tensor networks are proposed to describe some state that has similar entanglement properties as the holographic CFT. That was the motivation. So this was given in this work by Patrick Hayden, Separate Nizami, and Nathaniel Thomas, Michael Walter, and Xiao-Liang and me, where we propose these random tensor networks, and this is based on the earlier networks discussed by Brian Swingle and Happy, Daniel, Hello et al. So these tensor networks are designed in this way. So here I want to present it in a slightly different way from what you usually hear, because I want to emphasize actually we have states that are more general than random tensor networks. I would call it generally randomly projected states. So the general idea is you can introduce some parent state, which is a state of 2 kinds of qubits. One kind of qubit you call physical or boundary. In the holographic case, it's a boundary qubits, and this is your physical system. And the other kind of qubits lives in the bulk, and they are auxiliary. So I just call them A and B. And I haven't said anything about the parent state. So the state can be any state, and there's some entangled state between them. And then the physical state I want to consider is not this state, but it's generated from this state by doing random projections on every auxiliary qubit. So these are auxiliary qubits, which have some dimension d. So when you project so you can think of this projection as like measurement and then select on one of the measurement results. And so when you do that, you remove these qubits from your Hilbert space. Or you can think, if you do that in your lab, you measure these qubits into some random basis, and then you get one of the results. Then these qubits become pure states. The pure states in different random bases, and each of them are in different random states. And then after you do that, then this physical qubit got decoupled from these auxiliary qubits. But as a consequence, the physical qubit enters a different state, which may have more complicated and richer entanglement structure. So this whole mechanism is a way to generate more non-trivial kind of quantum entanglement from a simpler entangled state. That's the whole idea. This psi p can be anything, but it's only useful when psi p is simple enough so that you know its entanglement property. And we are going to see how the entanglement property of these two things are related. And the random tensor network, what we usually call random tensor network, is a special case of that, which is when psi p is a bunch of EPR pairs. That's the simplest possibility of entangled state. So if your psi p is a bunch of EPR pair states, each of these lines represent a pair. There's EPR pairs between the physical state and the auxiliary, and also between different auxiliary states. And then so it looks like this in a 2D picture. So you have these EPR pairs, and then you project on all these sides. Then the projection removes these auxiliary qubits from the Hilbert space, but also mediate some more non-trivial entanglement between the physical qubits. So that's the special case of this random projected state. Okay, so now let's see why these states are useful. It's mainly useful because we have some way to calculate their entanglement properties, at least in the sense of random average. So let's look at these kind of local unitary invariants which are polynomial. Look at these invariants which are expectation value of some operator in k copies of the system. We have seen that Rényi entropy and the Rényi negativity are examples of these. And in general, you can make more complicated examples, are more multipartite entanglements by putting different HX here. The different HX are just different permutation elements acting on different legs. Like you can have some region on the boundary, and you put a permutation on each of them, and the permutation can be different. Okay, so that's the general quantity we want to calculate. And the key point is that quantity, if you write the physical density matrix as the parent state density matrix with projections, then it looks like an expectation value in this parent state, k copies of parent state. Expectation value of some operator, which is these permutations on the boundary and the projectors in the bulk. And then the key point is this formula that's known mathematically, that when you average over k copies of the projection, you get a sum over permutation. And that's because that's the only thing that's invariant under permutation and unitary. I mean, this average, when I average over states with a measure that's invariant under unitary, I have to get something that's invariant under unitary. And this is the only choice, it turns out. So it has to be this form. And as a consequence of that, you map this kind of local unitary invariance to a sum over many terms, and each term looks like a local unitary invariant of the same form in the parent state. Because this projector also becomes some kind of a bunch of permutation operations on every site. So you just get permutations in the bulk and permutations on the boundary, and then you're summing over all these G's. So this problem looks like now looks like a partition function of some spin model, and the partition function is determined by this entanglement properties, these local unitary invariants in the bulk in the parent state. So for any given parent state, I can just calculate this for different permutation group elements and define that to be an action of my spin model. When I say spin model, I mean the spins lives in the permutation group. So at every vertex in the bulk and boundary, I have a spin. And the boundary spins are fixed by what I want to calculate. The bulk spins are fluctuating. So, and you're calculating their partition function. So this mapping is very general. And so you map some entanglement properties of the boundary to some entanglement property in the bulk. And the particular thing, when you take this very simple parent state, which is EPR pairs, the particular thing there is the spin model has a two-body interaction. Because it's only EPR pairs, all the entanglement is just sum over the contribution of each pair. So that translates into the statement that the spin model has a two-body interaction. For example, we don't need to go. So for example, if you take K copies, then these EPR pairs give you an interaction between these permutation spins that looks like this simple form. The form it has some coefficient which is like inverse temperature that's controlled by the bond dimension, log d, and this quantity is basically a measure of distance between the two permutation elements. Say, on the tensor network, I have this gx on every site, and then I'm looking at the neighboring sites, and then it's really just like an ordinary sigma model. So the interaction is determined by the distance between them, and the distance is simply measured by how many transpositions you need from one to the other, or how many transpositions you need from gx inverse gy to identity. So like you count. Like for example, cyclic permutation has k minus 1, and the identity is trivial. Right? So that's a simple definition of distance. And then you got this spin model, and when you calculate different properties on the boundary, you just put different boundary conditions to it. For example, for Rayleigh entropy, you put a boundary condition that's cyclic permutation here and the identity there. Then the partition function at a low temperature, which means large bond dimension, is dominated by a configuration that only has 2 domains. I mean, these discrete spin models, it has domains, right? So domain means all the spins here are cyclic permutation, and all the spins here are identity. Then there is the energy cost that only comes from the domain wall, which is the place where you are doing different operations on 2 ends of the link, and that gives you some contribution like this. It's like gamma r is just an area of domain wall, which is just counting how many links are on the domain wall, and each link basically just contributes the Rayleigh entropy of that link, which is this log d times k minus 1. So that's like playing the role of a tension of a brane. So in general, you should sum over all these different configurations, and each configuration has a contribution like this. And in the large bond dimension limit, when the bond dimension is really large, then this is dominated by 1 configuration. So in general, you don't have to just have 2 domains. You can have other domains which are doing other things in the bulk, and as long as you keep the boundary condition. But it will be dominant by this simplest configuration in the large bond dimension limit. So now let's just apply all these things to the negativity case. So in the case of a negativity, it's really just a different boundary condition from Rayleigh entropy. So let's say I have some boundary like this, and I'm taking 2 regions, C and D, and then look at negativity. That's in row CD, you do a partial transpose of D. By the way, if you take D to be the complement, so CD together is pure, then negativity has some simple relation with entropy. So that's not a non-trivial case there. So the non-trivial case is when you have basically 3 regions. That's why I want to say, in some sense, negativity is measuring some multipartite entanglement, although it's by definition, it's some bipartite quantity. It's measuring how there is quantum entanglement between C and D. But because it matters where is D, like it's not a property like entropy, which only knows about C. So if you partial trace over D, then this will change. So it, in some sense, start from the pure state, it measures something multipartite. So the boundary condition is the cyclic permutation in C and the opposite cyclic permutation in D. And when you look at that boundary condition, you cannot have that simple 2-domain configuration before. So there is a new question, like with this boundary condition, which is 3 different values, cyclic permutation, opposite cyclic permutation, identity, what happened? Is it like 3 domains, and then you minimize the sum over domain wall area? Or is it like something more complicated, like something emerge in the middle, or I'm just drawing different possibilities here? And the answer is actually this one. It turns out to be this rather than the simplest like 3-domain picture. And the reason, and this was first studied by Sepra and Michael in 2016 for the case of k equals 3, and they studied it in the random stabilizer code, but it's mathematically very similar to this case, the random tensor network. And they were interested in how many multipartite entanglement there are. So when you look at the general K, what happened is there is some property of the permutation group that you can always find an element tau in permutation group. You can find multiple of them. There's some element tau such that all paths from the identity to the cyclic permutation go through tau. And tau is also on the path from xk to xk dagger and from xk dagger to identity. So if you draw the graph, like these means the transposition. Like I have some distance in the group of permutation. Then this distance, like the shortest path between these three domains, actually goes through some common elements. And as a consequence of that, that means my domain actually can split, and without costing energy. Like if you have a tau that's not on the minimal path, then if you go from xk to tau and from tau to I, you will cost some energy. But so you may not want to split. But here with the tau that's on the minimal path, you can add in this tau domain, and it doesn't cause an increase of the tension. The tension of the red domain and the purple one together is the same as the black one. So then you just then there is nothing stopping you to split the domain, because this one has a bigger area than that, right? So once you can split the domains, you can just minimize the area, and then you get three minimal area surfaces. So this is the most economic solution, and that gives you an example of tau. For example, is some cyclic permutation which involves part of the elements. Say for k equals 7, you can cyclic permutation over the first 4, and then you do some other permutation over the other over another 4, and then you get the cyclic permutation. So that's the intermediate step. And similar thing happens for k equals to even. You can take half of them and do that, and then take half. Say for k equal to 8, you can cyclic permute 4 and then permute 5. Okay, so once you know there are these kind of taus, then you can write down what is the contribution to the action for this configuration, and that just gives us the answer for the log of negativity, for the log of Rényi negativity in the large D limit. So here I'm assuming, say, the geodesic surfaces are all unique, so there is one surface which is dominant the contribution in large D. So if that's the case, then you get this log D factor times some surface tension, and then this area of each of them. There is a difference, though, between the even case and odd case. So in both cases, what you are doing is you want to find the tau so that the tension of this brain plus the tension of that brain is the tension of brain between xk and 1, which is k minus 1. So in the odd case, you can divide them equally. So all the three brains have half tension, which is k minus 1 over 2. And in the even case, what happens is the cyclic permutation to the inverse of it has a different tension from that one. So it has to be divided asymmetrically. So there's some asymmetry here where two of them has a tension that's proportional to k minus 2, the other one is k. But anyway, these are just something you can easily work out with some simple math. And the answer is, okay, we got a formula for the log of negativity for both the even case and odd case. And then we can just take the analytic continuation simply. Right? So for example, okay, before that, I just want to emphasize, that I have been drawing the three region case where the two regions are neighbor to each other, but that's not essential here. Like when you have two regions that are not neighbor, and then you run the same argument, you will also find, okay, I have one domain here, one domain here. This is the third domain. Then there is a tau in the middle. But if you have a case where, say, the two regions have no mutual information, say the minimal surface bounding CD is just this one, then there is no need for that middle domain tau. Right? So this is already the minimal energy configuration. Like that's not available here. Like you cannot just have a domain here because these two are different. Right? You have to have something in the middle. So basically, it applies to the general multi-region case. And when you don't have mutual information, you will just simply get the log nk is the same as the Rényi entropy, which is the same for separable states. So okay, so with this log nk, you can do analytic continuation. And for example, the logarithmic negativity is given by taking the even one and then take n goes to 1. Just assume 1 is an even number, and then you get something like this. You get, say, go back to this formula and take k equal to 1, then you get like this minus the other 2, and there is a minus sign in front. So what you get is a mutual information with a 1/2. So you see, so in the random tensor networks, log negativity is simply proportional to mutual information. I think that's saying that all the mutual information comes from quantum entanglement rather than classical correlation. I don't know whether that statement is precise, but at least they are simply proportional. So mutual information usually can come from classical correlation too, right? So, but here they are all contributing to negativity. But we can also look at the other quantity, which is this transposed entropy, and that's basically like the entropy. Like you look at this odd case, which correctly goes to 1, goes to 0 if k goes to 1. But you can take a derivative there, then you get this thing, which is the sum over 3 entropies. It's a sum over the entropy of C and the entropy of D and the entropy of CD together. So now if you compare that with the entropy without transpose, which is just the entropy of CD, the difference is also half of mutual information. So although these two measures are generically different, in this case, they give you the same answer.
Sorry, but this is a feature because of the tensor networks, right? Because in general, the log negativity is not given by the information.
Right. In general, they are certainly not equal because, as we said earlier, if you start from a separable state and gradually deform from it, this thing will stay 0 until there is some eigenvalue cross 0, and this one will immediately become non-zero. So for random tensor networks, somehow all the entanglement all the correlations are quantum entanglement, I would say.
But again, this is a feature also of the fact that all the Rennies are the eigenvalue spectrum is flat.
Right. So here, yeah. So in the simple random tensor network, it also these simple results also depend on the fact that all the Rennies are the same. And actually, we can change that. I mean, we can just put it instead of EPR pair, we can put some more general two bipartite entangled state. And then what happened is in this formula, instead of putting log D, you just replace log D by the Renyi entropy of that EPR pair. And yeah, actually maybe it's more useful to write down that formula. So what shows up will be different Renyi entropies on the different places. Like these three will all be the same Renyi entropy, which is like the Renyi of k plus 1 over 2. And this one will be some Renyi entropy of the EPR pair, and this is another one, which is this is k over 2 plus 1, this is k over 2. Right. So in general, you can take care of non-flat entanglement spectrum, but still it's different from the holography case, because the minimal surface will stay where they are, independent from what range you look at.
But all the ranges are proportional to each other somehow.
Sorry?
All the ranges are proportional to each other.
The range is, if the minimal surface stays where they are, they will be proportional to each other. You can actually make them not stay in the same place by making the ranges very different. Like these pairs here have a range that strongly depends on k, and here it doesn't depend on k. So then when you change to a different k, you may go to a different place. It's possible, but I think there is still a key difference between that and the gravity case. I'm going to say the gravity case. Like in the gravity case, if you look at the ranges, there's some long-range interaction, which is gravitational interaction. And that's the thing that's missing in this simple EPR pair states. Clearly, nothing is long-range entangling with that. But you can modify that by changing to a different parent state, maybe with some long-range correlation. Yeah. Okay. So. Okay, so now let me discuss what happens to ADS-CFT. So we want to use this knowledge about random tensor networks to speculate and make some conjecture on ADS-CFT case. And as we just said, the entanglement properties are different. Like in the random tensor networks, at least in the simple case. Yeah, actually, this is a good way to make the statement. Even if I make the link states have a sk that's dependent on k, it's still true that the minimal surface here has nothing to do with the minimal surface there. So the entropy, the Rényi entropy will be a sum of the two if the minimal surfaces do not connect to each other. And in the gravity case, according to this work of Xidong, his proposal is if you don't look at Rényi but look at some related quantity, which is a derivative of Rényi in some sense, that thing is proportional to an area of a brane. But when you solve the problem with some branes here, then the branes interact with each other, so there is an non-trivial mutual information in the Rényi. So that shows how you go from tensor networks to gravity and what's the difference. And similar things should happen for negativity in a more complicated way. So so in the simplest case, if you have if you have adjacent intervals in 1 + 1 CFT, then the situation is simple because it's a 3-point function of twist operators in CFT and it's completely fixed by conformal invariance. So you just need to know the scaling dimensions of the twist operators and you know the results. And it sort of looks like a sum over 3 minimal areas with different coefficients. But the question is, how do we generalize that? So the 4-point case is much more difficult when we have two regions that are separate. We don't have a rigorous story here. Yeah?
So for the usual Rényi, if you have two intervals, the Rennies are like the hydrogen coefficient function?
Yes.
Does that match to the negativity?
It's still homogeneous. Yeah, it's the topology is the same. Because what happened is, for two intervals, if you are calculating Rényi, you are doing the twist operator like this, and then in the negativity, you're just doing this. Yeah, it's topologically the same higher Riemann surface, but with something like a Dan twist from the original one. There's some modular transformation from the Rényi one. I think it may be possible to calculate that when you assume something about the correlation function. In general, we don't know how to compute that. Okay, so let me describe what is a possible thing that happens. So if we think of like how to calculate this thing in gravity, then in the Rényi case, in the entropy case, we will just put some boundary conditions which are conical defects, and then look at the corresponding bulk geometry, and then usually you do a quotient so that the boundary is smooth, and then put in some brane in the bulk, and like that's what like for example this work of Xi has used, but here it's complicated to do the quotient. I mean, we don't. It's not obvious we can do any quotient because this, like, you go from some permutation to some other permutation, and these permutations are not really invariant under ZK. So if we don't do the quotient, what happens? I mean, it's a well-defined setup. Like you have this boundary with this conical defect, with the 4 conical defects like this, and then you can imagine you first put in a geometry that have the same kind of conical defects in the bulk, and then that's not a solution of Einstein equation. Then you let the solution relax to some solution of Einstein equation, which will smooth out these conical defects except at the boundary. So it's like this picture, which you also see in the Lukovic Marcina's work about proving the RT formula. So I imagine the geometry looks like this. Like, I don't really have any singularity here, so I draw it as like a fat brane. So it's really smooth there, but you know it actually comes from. You can imagine this as start from some geometry with a conical singularity, and then you relax it, and it becomes smooth here. So you know what you know is that if you go far away around this region, then you get a conical deficit angle, which is determined by this twist. So it's some value for even and some value for odd. And these statements are not rigorous because you may have to go infinitely far away from the brane and you may not have enough space. But it becomes better in some limits. Okay, so let me first writing down some hand waving thing. Like because the smearing here is really the same as what happened in the Rényi calculation, where in the Rényi calculation you can really do it by doing the quotient, but if you don't do the quotient, then you know, like if you don't have the other 3, you know what this geometry means. We know how to solve this in principle. So if we ignore like these things are interacting with each other, then this thing will look like a sum over some ranges. And the thing that we really, the reason why this is not an equal sign is these different regions interact with each other, so that we don't know a general formula, and it's not going to be a simple sum. But there are some limits which are better. Because let's say the simplest limit is actually the transposed entropy, which is the odd case when k goes to 1. Because that's the only case where all the branes has a vanishing tension. Like when you look at this formula, like in the even case, there is always some brane with a finite tension. But this one, all the 3 branes have the same deficit angle, and you can make deficit angle go to 0 for k, for k goes to 1. So that's really like the von Neumann entropy calculation. Like in that limit, the curvature you introduced to your geometry by your boundary condition is very small. So I expect that this effect of relaxing the geometry and making it satisfy Einstein equation, that effect will only affect a small neighborhood around this region. So the back reaction is getting vanishing in that limit. Right? So in that limit, this picture becomes precise, and you really just get sharply defined minimal surfaces. So your branes become like probe branes. So in that limit, we expect the entropy formula. We expect the transposed entropy. Sorry, this should be S transpose. The transposed entropy will be simply half of sum over 3 entropies, SC plus SD plus SCD. This is the case we are most confident about. And then there is a slightly more difficult case, which is if you take the even case and take k goes to 2. This is again not the log negativity. Log negativity is like the most difficult thing. So if you look at this formula and take k goes to 2, then 2 of the branes becomes probe branes. Like they are not they are very light and they don't contribute to back reaction. So you only have the third one. But with only one twist, with only one brane, we know how to solve it. It's the same as the Rényi calculation. Right? So in that case, you have this purple one, which is something with a finite twist. So you have to solve the geometry. It's not a probe brane. It's not a minimal surface. But you know how to solve that. And once you solve that, then the other 2 are just minimal surface in that geometry. So you actually get a formula if you take derivatives of this quantity. This is just following what Xi did to extract the area of these branes. So what you get will be like a sum over some minimal surface areas and the area of this brane. And the difference is these are just minimal surfaces, and this is not minimal surface. This is a brane with some finite mass density. Okay, so that's another case we can be comfortable making a conjecture about. And then the most difficult case will be the logarithmic negativity, because all the 3 branes have finite tension, and they really have non-trivial back reaction. So we really don't know what exactly happens there. And by the way, if you compare with the adjacent interval case, you see the naive formula you get by assuming they don't talk to each other is indeed wrong. So there is some non-trivial back reaction. So that we don't know what can be done there, and it's an open question. So okay, so that's the end. And in summary, we find that you can study these things, negativity-related quantities in random tensor network and make some conjectures on their behavior. But also the interesting thing is you can make some new characteristics of the non-separability of state. And these characteristics are actually easier to study. And there are many open questions. Thank you.
Do you have an intuition what happens in higher dimension? 2 plus
higher
1?
Dimension?
Yeah.
Well, all these discussions are in higher dimension, except I mentioned that the 3-point function value result, that's special to 1 plus 1 CFT. But like all the general,
because in 2 plus 1,
these conjectures we make,
yeah,
they don't depend on 3D. Because we didn't use the fact that like the twist operator on the boundary is a point like, or we don't need that. It's just like the Lucquez-Martesina calculation for RT formula. Like you don't have to restrict the 3D.
Any other questions?
when we get k not goes to not goes to 1/2 or not goes to 1. In this case, when we define it, we need a transport from the bar state to can state, can state to bar state. But why I didn't see it in the holographic calculation?
Because we calculated these replicated quantities, which basically independent from the choice of the mapping. Like when you look at the trace of the partial transpose to power k, that's independent from how you define the transpose. In general, the definition depends on the basis choice, but that's only up to a local unitary. So in the end, it becomes just a correlation function.
All right, so let's thank Xiao-Liang again.
Thank you.